Everyone. In this video, we'll study how we can use matrices and linear algebra to find the coefficients beta naught and beta 1 of linear regression. For every data point xi, yi, we can write the equations of linear regression as yi hat is equal to beta naught plus beta 1 xi, which can be rewritten as yi hat is equal to 1 into beta naught plus xi into beta 1. Now pause and think of a way to represent this using matrices. Can we treat it like a matrix product in this way? Yi hat is 1 cross 1 matrix, which is equal to the matrix product of 1 cross 2 matrix, that is 1 xi as a row matrix, and 2 cross 1 beta naught and beta 1 as a column matrix. So if you perform the matrix multiplication, that is the exact equation that you will get. So we have successfully converted this equation into a matrix product in terms of matrices. Now this looks perfect as per the matrix multiplication rules, right? Now let's write this for all the data points. We will have to account for errors too, right? So when we are taking it to our data set, we actually have yi. What we are finding in this equation is yi hat, and we know the relation yi is equal to yi hat plus epsilon, if epsilon is the error. So y1 is equal to 1x1 beta naught beta 1 plus epsilon 1. y2 is equal to 1x1 multiplied by beta naught 1x2 multiplied by beta naught beta 1 plus epsilon 2. y3 is equal to 1x3 multiplied by beta naught beta 1 plus epsilon 3. Now let's stack together the three matrix equations. We can stack them together as y1, y2, y3 can be stacked together as the output vector y. 1x1, 1x2, 1x3, these three rows can be put together or stacked together as the design matrix x. And beta naught beta 1 is common in all three equations as it is, so it can be kept as it is. This is the coefficient vector beta, it is a column vector again. And we can also stack together epsilon 1, epsilon 2 and epsilon 3, which is the error vector. Now the same thing can be written as y is equal to x beta plus epsilon, where each of them is a matrix. Now say you have 1000 rows of data and let's say 7 features, x1, x2 up to x7. Okay, then you can write it in matrix form as follows: the column vector y1, y2 up to y1000, because you have 1000 data points, and the design matrix, each row will have 7 plus 1. The first element is for the intercept, and then you have 7 for the 7 features, right? So each row will have 8 elements, 1 and the 7 features. So first row is for the first data point, second row is for the second data point, and accordingly it will have 1000 rows for the 1000 data points. And that is multiplied by the column vector beta naught beta 1 up to beta 7. Beta naught is the extra one for the intercept, beta naught is the intercept, and beta 1 to beta 7, they are the coefficients of x1 through x7 plus the errors epsilon 1, epsilon 2 up to epsilon 1000. Okay, in general, if the data set has n rows and p features, then the linear regression problem can be represented as follows. Firstly, we'll have the column vector y1, y2 up to yn, because there are n rows or n data points or n responses, and the design matrix will be n cross p with n rows and p columns. In fact, there will be p plus 1 columns, because one column, the first column, will be all ones for the intercept, and then there will be p columns for the p features. So it will be n cross p plus 1 dimension design matrix x, and then there will be the coefficient column vector, which is beta. It will have beta naught beta 1 up to beta p, and then there will be, so in addition we'll have the error vector, that is epsilon 1, epsilon 2 up to epsilon n for the n data points. In the next video, we'll actually try to solve this.